When you look at a petrol and a diesel engine, upon first glance they look very similar. And that makes sense because after all, both are internal combustion engines. They do their combustion internally, which results in them having very similar anatomy. Both petrol and diesel engines have a cylinder block and a cylinder head, some camshafts, some valves, some pistons, a crankshaft, and some rods. The anatomy is very similar. What's different is the way they do their combustion. And a more accurate term to describe petrol and diesel engines is actually spark ignition and compression ignition engines. Now, all commercially available petrol engines are spark ignition engines, meaning that they have a spark plug in the combustion chamber. And what the spark plug does is, well, it creates a spark. Now, to create a spark, the spark plug needs voltage, and the voltage is supplied by the vehicle's ignition system. On older vehicles, the ignition system consists of a distributor and an igniter, but on newer vehicles, the ignition system is distributor-less, and instead we have coil packs or a coil-on-plug ignition system. But regardless of the kind of the ignition system, they all work the same way. As we said, they provide voltage to the spark plug, a lot of voltage, usually in excess of 20,000 volts. And what this voltage does is that it starts ionizing the gases or the air-fuel mixture in the spark channel. And what this does is that it converts the gases from electrical insulators to electrical conductors, allowing a current of electrons to arc from the main electrode of the spark plug to the side or ground electrode of the spark plug. This current of electrons intensely raises the heat in the spark channel, and it causes the gases there to rapidly expand outward. This starts a chain reaction known as deflagration. Now, deflagration is a bit of a weird word, but what you have to know about it is that it's a combustion process that occurs subsonically through heat transfer, meaning that the first layer of hot gases transfers the heat to the next cold layer, and so on until all of the gases are burned away. From an engineering perspective, deflagration is good and desirable because it's pretty even and controllable, and it's ideal to get an object moving, for example a piston in a cylinder bore. Now let's see how a diesel initiates combustion. Well, in a diesel engine there's no spark plugs, no spark, no ignition coils, none of that. A diesel initiates combustion purely by compressing the air. The air in a diesel engine gets compressed to a much higher degree than in a petrol engine. And as we know, as the air gets compressed more and more, it also heats up. And as the piston in a diesel engine reaches top dead center, the air gets so hot due to the compression that it's hot enough to ignite the diesel fuel as it's introduced to the combustion chamber. And this is why a diesel engine is also called a compression ignition engine. What creates ignition is the compression of the air. And what's different isn't just the way combustion is initiated, it's also the timing of the introduction of the fuel into the combustion chamber. A petrol engine introduces fuel earlier than a diesel, during the intake stroke of the engine, and the fuel and air inside a petrol engine are already properly mixed before the spark plug fires. Compared to this, a diesel introduces fuel much later, during the compression stroke of the engine. Fuel can only be introduced when the air is hot enough to ignite the fuel. And of course, the air is hottest when it's most compressed. And this is why the diesel only introduces fuel very late in the compression stroke, just before the piston hits top dead center. Unlike petrol engines, which can feature port injection or direct injection or both, a modern diesel engine almost always features only direct injection, meaning that fuel is directly injected into the combustion chamber using some form of nozzle or more commonly an injector. And when a diesel injector fires, it sends a mist of very small droplets of fuel into the combustion chamber that is now filled with highly compressed, very hot air. This is the beginning of the injection process. As the fuel droplets meet with the hot air, they start to vaporize and mix with it. The piston continues to travel towards top dead center, further compressing the air, which now reaches a temperature high enough to ignite the vaporized fuel. At this point, rapid ignition of the small amount of premixed fuel and air occurs. The time between the start of the injection and the start of the ignition is called the ignition delay in a diesel engine. The rapid ignition that occurs at the end of the ignition delay creates a sharp cylinder pressure spike. This rapid ignition of the initial premixed fuel and the sudden increase in the combustion pressure is what generates the characteristic knocking or clattering sound of the diesel. This initial part of the combustion process is also often called uncontrolled combustion because combustion may start at any one or multiple points in the chamber. As injection continues, the new fuel is sprayed into an already burning mixture, which dramatically increases the rate of vaporization, and this fuel starts burning almost instantly after it leaves the nozzle. Because the uncontrolled combustion stage has raised the temperature enough and created enough turbulence that combustion in the following stage can be controlled by controlling the injection. This part of the combustion process is also called controlled combustion. After the injection process is finished, some fuel molecules that fail to create a combustible mixture will remain unburned in the chamber. These less volatile molecules will undergo combustion as the piston travels further down the bore, and most will be burned away by the time the piston reaches bottom dead center. Now that we have seen the differences in the combustion process of petrol and diesel engines, let's see how these differences result in these two different engines having very different natures and being good at different things. Now, one of the key differences between petrol and diesel engines can be observed without even looking at the engine. All you have to do is sit inside the car and look at the tachometer. Petrol and diesel engines have very different redlines. Most diesels rev to anywhere between 4.5 to 5,000 RPM. Compared to this, petrol engines rev much higher, anywhere between 6 and 9,000 RPM. Now there's three main reasons why diesels don't rev as high. The first reason, and the one that's easiest to understand, is that diesel engines require heavy, beefy, strong internals. They need strong internals because they experience much higher combustion pressures compared to petrol engines. What's especially important are those combustion pressure spikes that occur during the uncontrolled combustion process we just covered. If the engine internals were fragile, they would simply fall apart during the uncontrolled combustion process. This is why diesels need strong and therefore heavy internals. But heavy internals have a price. They are harder to spin and they limit the max RPM. The second reason why diesels don't rev as high is that most diesel engines are under square by design, meaning that they have a much longer stroke compared to their bore. And although this is good because it allows diesels to make a lot of torque early in the rev range, it also too limits max RPM potential. But the third and perhaps most important reasons why diesels don't rev as high is that they can't really control ignition timing. A petrol engine that has a spark plug and an ECU and an ignition coil can fire the spark plug at any point in the compression stroke of the engine. This is called ignition advance, and petrol engines rely on it to keep making power at higher engine speeds. As the RPM increases, so too does the speed of the piston, and the spark plug is going to fire earlier in the compression stroke to account for the increased speed of the piston, to make sure that the flame front starts fully propagating and that maximum combustion pressure is generated at the right time, when the piston starts moving down the bore. Now, a diesel engine can't do this. It cannot have a wide range of ignition timing control because it cannot start the combustion event sooner or later than when the air is fully compressed. And the air is always fully compressed at the same point in the piston's travel, at top dead center. And although diesel engines do have injection timing, due to the compression ignition nature of the engine, the range of injection timing is much more narrow compared to the range of the ignition advance of petrol engines. And this is why diesels usually stop revving right at the point where petrol engines start incorporating more and more ignition advance. Now there's another factor on top of all of this, and that's that diesel fuel burns slower than petrol fuel, and this is another reason why high RPMs would essentially be wasted on a diesel. At high piston speeds, the piston speed would actually be too high, and the slowly propagating flame front of the diesel would miss the piston. By the time maximum combustion pressures were generated, the piston would be too far down the bore, and the diesel would actually make less power at higher RPM. But thinking that not revving high is a failure on part of the diesel, would be wrong. The diesel doesn't rev high because it doesn't need to rev high. It does everything it needs to do at the low RPMs it has. And although this does result in a more narrow power band compared to the petrol, it does have a very important benefit. Diesels are long-lived. The heavy internals, strong internals, and the low red line help diesels last a long time. We all know that engine wear exponentially increases with RPM, and this is why on average diesel engines last longer than petrol ones. When the piston inside your engine is at the bottom of its travel, at the bottom of its stroke, at bottom dead center, that's the largest cylinder volume of your engine. When your piston is at top dead center, that's the smallest volume of your cylinder. The ratio, the difference between these two volumes, determines the compression ratio of your engine. And it's a very important number for every engine because it determines a lot of things for the engine. Now, when it comes to diesels, diesels have a much higher compression ratio than petrol engines. And this results in one of the few very noticeable anatomy differences between petrol and diesel engines. Here we have a combustion chamber of a petrol engine. And here we have a combustion chamber, or lack thereof, in a typical modern diesel engine. Here we have a typical modern petrol engine piston. And here we have a typical modern diesel engine piston. As you can see, the smallest volume in a petrol engine is achieved by the combustion chamber. However, this volume would be too large for the diesel, so it uses instead a void in the piston to achieve the smallest volume of its cylinder. And of course, the void in the piston is smaller than the combustion chamber, leading to a smallest volume of a diesel, which results in a higher compression ratio. Now, a higher compression ratio is better because the more you compress the air and fuel, the smaller the area in which it combusts, the higher the force applied onto the piston. To help you visualize why a higher compression ratio is better, you can imagine a stick of dynamite being detonated in two different rooms, one small room and one large room. So what do you think? The walls of which room are going to see more damage from the explosion? Of course, the walls in the small room, because they're closer to the source of the expanding explosion of the energy. And the same thing happens in an engine. The closer the piston to the source of the combustion, the more force is going to be exerted on top of the piston. And that means that with a higher compression ratio, you're making more power. It also means that your engine is more efficient with a higher compression ratio because you're harnessing more energy from the same amount of air and fuel. So why don't petrol engines run the high compression ratios that diesel engines have? Well, they can't, because they're knock limited. Now, the combustion process inside the petrol engine should only be initiated by the spark plug, and all the air and fuel should be burned away only by the propagating flame front. When combustion spontaneously occurs outside the flame front in a petrol engine, that's called knock. Knock sharply raises the combustion pressures inside the engine, and if it continues to occur over time, it will destroy a petrol engine. This is why, of course, it's undesirable. Now, knock can occur inside a petrol engine because the petrol engine is compressing both air and fuel. And if there's enough compression or too much of it, if the temperatures get high enough, then the mixture can spontaneously combust outside the flame front. And this is why petrol engines must maintain lower compression ratios to account for knock and to prevent it from happening. Compared to this, a diesel engine is compressing only air. There's no fuel, so there's nothing that can spontaneously combust. Inside a diesel engine, fuel is introduced only when combustion is supposed to happen. This is why knock isn't an issue inside a diesel engine. Because they don't have to worry about knock, diesels can run a much higher compression ratio, anywhere between 15:1 to 23:1. Compared to this, a modern naturally aspirated petrol engine usually has a compression ratio between 11 to 12:1. Although there are some outliers that run 14:1 compression ratios, they are an exception, and the average is between 11 to 12:1. As you can see, much lower than a diesel engine. But forced induction petrol engines have to run an even lower compression ratio ratio between 8 to 5 to 10 to 1, because they have to account for the fact that the turbocharger or supercharger is sending in already compressed air. And if you compress it even further, increase its temperature even further, then the chance for knock increases. And this is why forced induction petrol engines have to account for this and compensate with a slightly lower compression ratio. This is also why tuning forced induction petrol engines is more challenging than tuning a forced induction diesel, a turbocharged diesel, and this is why you can run more boost with less risk in a diesel engine. Now let's see how all of this results in diesel engines being better at making torque and petrol engines being better at making horsepower. Now, torque is essentially force applied at a distance. This is what the measurement units for torque express after all. When you're tightening down bolts with a wrench, you're actually applying torque to the bolts. The force is what you're doing with your hand, and the distance is the length of your wrench. This is why you use a longer wrench to apply more torque to the bolts, because you're increasing the distance in the force and distance equation, resulting in more torque. Now, the same thing is actually happening inside your engine. Your hand, or the force, is actually the combustion process inside the engine, which applies force on top of the piston. The distance, the length of the wrench, is actually the length of the connecting rod and the crank throws. Now, because diesel engines have more stroke, they need more stroke to compress the air more, they actually have more distance in the force and distance equation. And because they compress the air and fuel more, they generate more powerful combustions, which means more force in the distance and force equation, and all of this results in diesels making more torque. What is horsepower? Well, horsepower is torque multiplied by RPM. Now, petrol engines make less torque, but they rev higher, much higher, and this results in more work done over the same period of time, which results in petrol engines making more horsepower. Petrol engines typically have a thermal efficiency between 20 and 35%, with some modern petrol engines managing around 37 to 38% thermal efficiency. A 37% thermal efficiency means that 37% of the energy generated by combustion is turned into useful work. The rest is simply wasted as heat. Compared to this, diesels are more efficient and can manage a thermal efficiency of around 40 to 45%. So why are diesels more efficient? Well, the reason number one is, as we already said, compression. Because diesels are able to compress the air-fuel mixture more, they can squeeze more energy out of the same amount of air and fuel. The other reason why diesels are more efficient is simply because they use less fuel. Now, the stoichiometric air-fuel ratio for diesel fuel is 14.5 to 1. The stoichiometric air-fuel ratio for petrol fuel is 14.7 to 1. A stoichiometric air-fuel ratio is an ideal air-fuel ratio at which all of the fuel is burned away with none of the air left behind. So for a ratio of 14.7 to 1, we need 14.7 units of air for every single unit of fuel. When you increase the amount of air in this ratio, you're creating a lean mixture. When you reduce the amount of air in this ratio, you're creating a rich mixture. Now, petrol engines, depending on the load, can run on both sides of the air-fuel ratio. Typically, at idle and at cruise conditions, petrol engines run lean. But at wide open throttle, at full load, petrol engines must run rich, and forced induction petrol engines need to run even richer. Compared to this, diesels are very different. Diesels never run rich. They always run lean. Modern turbocharged diesel engines can manage an idle air-fuel ratio of around 160 to 1. As you can see, compared to petrol, this is extremely lean, and there's a lot more air in the diesel than fuel. And only at wide open throttle, at full load, do diesels sort of start to approach a stoichiometric air-fuel ratio, but again, even at full load, they are still pretty lean. And this means that inside a diesel engine cylinder, there's always more air than fuel. And this leads to a difference in how petrol and diesel engines modulate their power. When you press down on the throttle pedal in a petrol engined car, you're actually operating the engine's throttle body. The throttle body is a butterfly valve which dictates how much air is coming into the engine. The more you press on the throttle pedal, the more the butterfly valve is opened and the more air is coming into the engine. Then the engine's ECU uses various sensors to determine, based on the amount of air, how much fuel should be injected into the engine. When you press down the throttle pedal in a diesel-equipped vehicle, you're not operating any sort of butterfly valve. Instead, you're dictating the amount of fuel that goes into the engine. Now, don't be confused. Many modern diesels actually do have something that looks like a throttle body on them. But when you're pressing on the throttle pedal, you're not operating this butterfly valve. The butterfly valve on the diesels is actually used to improve the efficiency of the engine's exhaust gas recirculation system. So why don't petrol engines run with these same extremely lean air-fuel ratios as diesel engines do? Well, petrol engines can't do this because the air-fuel mixture in petrol engines is homogeneous. In diesel engines, the air-fuel mixture is heterogeneous. A homogeneous air-fuel mixture means that all of the air and fuel is evenly mixed. A heterogeneous or a stratified air-fuel mixture means that only one part of the air is mixing with the fuel in the diesel engine. And this allows them to run extremely lean. An extremely lean condition in a petrol engine is running a lot hotter and is also more prone to knock, and this is why petrol engines must avoid it. But another reason why diesel engines manage to be more efficient than petrol engines is the fuel itself. Diesel fuel is composed of longer chains of hydrocarbons compared to petrol fuel, and because of this it is more energy dense. For the same amount of volume, diesel fuel has around 15% more energy stored in it. But fuel efficiency is only one part of the economy equation. Now, diesel-engined cars and light trucks and other vehicles are typically more expensive to purchase when new. They're also usually more expensive in the used car market. Diesel engines are more complex, which means they're more expensive to manufacture, which leads to a higher end price for consumers. Another thing that has been changing for the diesel is that increased pollution awareness, as well as stuff like the Dieselgate scandal, has been driving change in diesel-related taxation and legislation, which means that it has been changing the resale values of diesels in various markets around the world. In some markets where diesels used to have a strong resale value, this has started changing and it's now hard to rely on the strong resale values of diesels. As a typical rule of thumb, you have to drive enough for a diesel to make financial sense. You have to cover enough miles to harness the increased fuel efficiency of the diesel. Otherwise, if you're not covering enough miles, a petrol is likely going to make more financial sense. Traditionally, the emissions of petrol and diesel engines have been presented as a trade-off between environment-harming CO2 and health-harming nitrogen oxides and soot particles. Diesels emit less CO2 simply because they use less fuel, but the high-temperature, high-pressure stratified combustion process in the diesel actually favors the production of nitrogen oxides and soot particles. Now, things aren't actually that simple and they aren't really black and white. Fact is that many air quality monitoring agencies across the world in different countries have done many independent road tests of equivalent vehicles equipped with equivalent petrol and diesel engines, and almost all of them have found that the CO2 emissions gap between petrol and diesel engines is negligible, usually around 3 to 5 grams of CO2 per kilometer. And when it comes to nitrogen oxide and soot particle emissions, modern diesel engines of a Euro 6 or equivalent emission standard are actually pretty clean because they have some very complex emissions equipment. Stuff like diesel particulate filters and diesel exhaust fluid injection are actually used to either trap or chemically convert the vast majority, more than 90% of the nitrogen oxides and soot particles. So when they're new, both petrol and diesel engines are pretty clean as long as they're maintained properly. Problems actually start to arise when diesel and petrol engined cars hit the used market. And this is where the diesel is at a disadvantage. Because the emissions equipment of a diesel engine is pretty complex, it's also very expensive. And the replacement of a diesel particulate filter on a vehicle that's 5 to 10 years old can amount to as much as 15 to 30% of the value of the entire vehicle. And this makes it very hard to justify this replacement for an owner of a used diesel vehicles. And this is why some owners look to less efficient but cheaper methods to temporarily lower their emissions just so they could pass an emissions test and continue driving their vehicles. And an emission test at the end of the day actually monitors the vehicle only once every 1 or 2 years. The remaining 364 days, the vehicle isn't really monitored and it's free to do quite a bit of pollution. Something else that puts the diesel at a disadvantage when it comes to pollution is that diesel engines are heavier and more complex, meaning that they use more materials and more parts to be made. And this is why their manufacture creates more pollution. On the other hand, diesel engines typically last longer before they need to be recycled. Now, fun is an entirely subjective thing, and the reality is that a lot of fun can be had with both a petrol and a diesel engine. That being said, on a tight, twisty road, it's very hard to argue against a petrol engine. It has a wider power band and a better soundtrack, and although it will give you less miles per gallon, on a road like this, it's going to give you more smiles per gallon. Another thing that works against the diesel when it comes to fun is weight. Diesel engines are typically pretty heavy, usually noticeably heavier than an equivalent petrol engine, and this of course negatively impacts the dynamic balance of a vehicle. And this is why, for example, front-wheel drive vehicles equipped with a diesel engine are always going to be more prone to understeer compared to the same vehicle with an equivalent petrol engine. But saying that diesels aren't fun would be very wrong. Diesels can provide the sensation of massive torque, and this can be very addictive. On top of this, diesels have greater autonomy, which means they can do more miles with the same amount of fuel, and this can be very important, and this is why diesels are your best ally when it comes to long distance adventure and exploration vehicles. And there you have it. That's pretty much it for today's video. I hope this comparison between petrol and diesel engines helps you better understand how they're different, why they're different, and how this impacts their different behavior and application. As always, thanks a lot for watching, and I'll be seeing you soon with more fun and useful stuff on the D4H.